Hello everyone. In today's video I'll be talking about a concept that is not directly linked to security and privacy, Bloom filters. They are used in Google's implementation of local differential privacy, RAPPOR. I am planning to do a video on RAPPOR, so I need to cover Bloom filters first. First, Bloom filters have been introduced by Burton Howard Bloom in 1970. Unfortunately, I could not find a picture of him. They are used when quick membership tests are needed, such as databases or spell checks. The basic idea behind a Bloom filter involves using multiple hash functions to map elements to a fixed-sized array of bits. And when an element is added to the filter, its hash values are used to set the corresponding bits in the array. When checking for membership, the hash values of the queried element are used to check if all corresponding bits are set. If any bit is not set, the element is definitely not in the set. If all bits are set, the element is probably in the set. Let's look at an example to illustrate this. Let's say you have a collection of email addresses and you want to quickly check if a new email address is already in the collection. Instead of storing the entire list of email addresses, you decide to use a Bloom filter to save memory. First, the initialization. Start with an array of bits. Initially, all bits are set to 0. Let's say you have an array of 10 bits for simplicity. Now, we have to choose hash functions, so we choose several independent hash functions. For example, let's use 2 hash functions. Each hash function takes an input, in this case the email address, and produces an index in the array. I have 2 exemplary hash functions here, so hash function 1 takes as input the email address and outputs the sum of all ASCII values and takes the mode 10, of course, so we are within the 0 to 9 value range because we have 10 bits. Hash function 2 also takes as input the email, of course, and gives or returns the number of vowels in the email, also mode 10. Now if we add an email to the Bloom filter, we apply each hash function to the email and set the corresponding bits in the array to 1. Suppose you want to add user@example.com, hash function 1 results in 4 and hash function 2 results in 6. So we set the bits at the indices 4 and 6 to 1. Remember, we take everything mode 10, which means we start at index 0 and stop at index 9. So this is how Bloom filter after one email address has been added. Now if we check for membership, to check if a new email, let's say new user@example.com, is in the collection, apply each hash function and check if all corresponding bits are set. Hash function 1 yields 4 and hash function 2 equals 7. So we check the bits at indices 4 and 7. If both are set to 1, the Bloom filter suggests that the email might be in the collection. However, this is not the case, so we can be sure that new user@example.com is not in the database. However, if the new email would be new user@example.com written like this, we have the same output for both hash functions as we had with user@example.com, which would result in a false positive since both bits are set. That's why we cannot say that new user with a Y is in the database, only that it could be in it. Now obviously our example is simplified and you would have much larger bit arrays than 10, but nevertheless false positives cannot be ruled out when applying Bloom filters. Their probability, however, decreases the more bits I use. More importantly, false negatives are ruled out, as we can be sure that the email is not in the database if those bits were not set to 1. In summary, Bloom filters have the following key characteristics. False positives. Bloom filters can produce false positives, meaning they may incorrectly indicate that an element is in the set when it is not. However, false negatives are not possible. If an element is not in the set, the filter will correctly report this. Space efficiency. Bloom filters use a small amount of memory compared to other data structures for representing sets. No deletion. Bloom filters do not support deletion of elements. Once an element is added, it cannot be removed. Quick membership tests. Bloom filters provide constant time complexity for membership tests, making them fast for large datasets. And that concludes today's video. Thanks for watching, share the video, subscribe to the channel, and I see you in the next video.